Hello class, in this short video we will learn about the operational amplifiers and different terminals that used in the operational amplifiers. So in today's lecture we are going to talk about a couple of things, very basic things about what are these operational amplifiers and how these operational amplifiers are very different with respect to the amplifiers that we saw so far using a transistors based, which are common emitter, common base and common collector, and why these operational amplifiers has a lot more advantages in terms of a circuit design, at the same time in terms of a circuit analysis. And we will look into the basic terminals of these operational amplifiers. And in general right now there are more than 2000 various operational amplifiers are available, and in this particular course that we are going to use an IC741 operational amplifier. So we will go through the terminals of those operational amplifiers. So the basic this particular video is going to talk about is operational amplifiers and their terminals. So these operational amplifiers, these are nothing but a normal amplifiers. Usually they are called as an op-amps in short. So op-amps mean for it's an operational amplifiers. So as we already aware of from the definition of an amplifier, so amplifier is a device that accepts an input signal and produces a linear output signal with a larger amplitude. So the only difference between the input of an amplifier to an output of an amplifier is the amplitude of the signal. So a good amplifier we talked about in the last class is it should keep the shape of the signal, meaning that it should be as linear as possible. So amplification is in terms of only with respect to the signal amplitude, but not in terms of a signal frequency or in terms of a phase. So these operational amplifiers can also work with the zero frequency signals, meaning that for a DC signal voltages. So these amplifiers can be used in order to increase the strength of your DC signal. At the same time, you can also increase the signal strength in terms of an AC signal for maximum of 2 megahertz range, and that's basically depending upon the type of amplifier. But what the name suggests is an operational amplifier. So the name suggests is these op-amps are very basic and used to perform some mathematical operations. So that's a way before the primary goal of these operational amplifiers is to perform addition, subtraction, integration and differentiation. So we will take a look into this circuit later on, but primary purpose of an amplifier is this is what they are used to be designed, but later on because of a circuit analysis is much simpler, these are used in order to amplify the signals as well. So integrated circuit fabrication technique. So basically we are going to look into how a circuit inside the operational amplifier looks like, but before we do that, the IC fabrication techniques are made high performance operational amplifiers are economical and more convenient to use. So when you look, this is the internal structure of an op-amp. The model number is LM741. As you can see, this particular op-amp consists of around 20 transistors and there are some diodes, some capacitors, some bypass capacitors are being used. But when you think of designing this operational amplifier on a breadboard, it's a complex task. At the same time, analyzing using all these transistors and see how they are connected to each other, it's a very, very complex. At the same time, it's going to be time consuming too. So as I said in the previous slide, IC fabrication technique. So the IC fabrication, so basically all these whole amplifier, so including of all these transistors, diodes, are fabricated in a very small single integrated chip, so that it will be very easy to analyze the signals. At the same time, it is very easy to design the circuits based upon those IC. and much more importantly, it will occupy very less space on your circuit board. So let's look at how an op-amp looks like and what is the circuit schematic. This is how an op-amp is going to be shown using a triangle symbol in the circuit diagram. And this is how an op-amp is going to be in terms of an IC configuration, and this particular configuration is called as a DIP packaging technique, which called as a dual inline package. So meaning that you will see here it's an 8-pin IC. So if you haven't used the ICs before, there is a way to identify the pin layout of an IC. For a dual inline package, usually you will see on the top left hand corner a dot. So from that dot, the pin terminals are going to be starting from 1. So it's go down this way, and 5, 6, 7, 8 down that way. So using that dot, you can specify whichever is the pin number 1 and through down the line, and it's going to be through the pin number 8. So any type of IC that carries a DIP package, this is how you can find out what's the pin number is. But let's look at what an op-amp has, what type of pins it has. So there are two inputs for an op-amp, which are called as an inverting as well as a non-inverting op-amps. As you can look, this is an inverting terminal, which is a negative terminal. So the name itself specifies it's inverting. So that's why it's a negative terminal. And the another terminal of an op-amp is a non-inverting terminal, and that's a positive. And there is one output for an op-amp and two power connections. This is a positive supply and this is going to be a negative supply. So when I observe on the IC, pin number 2 is an inverting input. As you can see, it's going to be specified on the circuit schematic. Pin number 3 is a non-inverting input. Pin number 4 is a negative supply, and pin number 7 is a positive supply, and pin number 6 is at the output. So these are the operational amplifier terminals, which are inverting, non-inverting, one output terminal, and two power supply connections. And this is this particular IC LM74. So this is the particular IC we are going to use throughout our lecture, and in the lab work too, we are going to use this particular IC. So if you can remember these IC layouts, otherwise you can find the data sheet in this particular link. And again, remember, pin number 2 is an inverting input, pin number 3 is a non-inverting, pin number 4 is a negative supply, pin number 7 is a positive supply, pin number 6 is an output. And if you can observe, there are some additional pins that I haven't commented on is pin number 1, pin number 8, and pin number 5. And you can see pin number 1 and pin number 5 has the same name. It says an offset null. Later on in our lecture, we will see what is meant by that offset voltage, because any electric circuit, if we consider, will provide some error voltage irrespective of whatever the temperature conditions is, whatever the input conditions are, or whatever the load is. So no matter what, no electric circuit is going to be ideal in nature. So how can we make sure that output should be as close as possible to an ideal output voltage? So that's what we are looking at. So we might use that pin number 1 and 5 in order to make the output voltage as close as possible towards the ideal point. And pin number 8 is NC, which means for no contact or not connected. So usually when you are following, when the IC is fabricating using DIP package, it's going to have an equal number of pins on either side. So that whole fabrication technique. So for example, inside this 8 pin or not connected pin, it's not going to be connected to any of the circuit internally. It's just there to support that particular fabrication technique or that particular IC packaging technique. So it doesn't have any significance in terms of usage, but it is just still there. It's just there to follow the DIP or DIP packaging technique. Alright, that concludes this short lecture.